Welcome to this lesson on modeling with arithmetic sequences. So today we're going to talk about how can you solve real-world problems using arithmetic sequences. All right, so we're going to start off with this problem here where we have a real-world situation where we have watermelons that cost $6.50 each at the local market, and the total cost in dollars of n watermelons can be found using C of n is equal to 6.5 times n. Right? So in this case, remember that this part right here gives us our term. The n itself is our position, or in this case, the position would be the number of watermelons. All right, so here we go. First, we're going to complete a table for the values of 1, 2, 3, and 4 watermelons. So I know that if I plug in 1, that's 6.5, because we can take off the 0, remember. 6.5 times 1 is 6.5. And 6.5 times 2, because I'm plugging in 2, is 13. Times 3 is 19.5. And times 4 would be 26. All right? So again, I'm moving to the next page, so I'm just writing this in here. It's the same page for you. I just needed more space. So I need to actually look at what all these pieces of information mean to me. First of all, I want to know what's the common difference. Well, the common difference here is $6.50. Yes, it's 6.5, but that 6.5 is actually the $6.50. All right, and then I want to know, what does n represent in this context? Well, it tells you here the amount of n watermelons. So I know that my variable, so n is representing the number of watermelons. So the number of watermelons. What are the dependent and independent variables in this context? So in this case, does the number of watermelons purchased depend on the cost, or does the cost depend on the number of watermelons? So think about it logically. How much you pay depends on how much you buy. So in this case, the dependent variable is the cost, and the independent variable is the number of watermelons. Right? The other way you can look at this, you know that your output is always your dependent variable and your input is always your independent variable. Okay, so we want to find C of 7. So in this case, we want to know what is C, the cost, when n, the number of watermelons, is 7. So I know I have to plug in 7, and I do 7 times 6.5, and that's going to give me 45.5. So I know that when I plug in 7, I get 45.5. So what does this value represent? This value represents how much the cost of 7 watermelons will be. And I'm going to type this so it goes a little faster. So this value represents the cost of 7 watermelons, which is, now we can't just put 45.5, we have to put $45.50. All right, make that a little bit smaller so it fits on the page. There we go. All right, so then now, what domain values make sense for C of n is equal to 6.5 times n in this situation? So what this is asking is what values overall, not specific values, but what types of values can you use for your inputs, for your domains? So I want you to take a second to think about this, pause, and then come back and check your answer. All right, so for this one, again, it would be only non-negative integers because you can't purchase negative numbers of watermelons. However, you can purchase half of a watermelon. Okay, so in this case, we have integers and not just whole numbers, but they have to be non-negative. So non-negative integers. Okay, so modeling the arithmetic sequence from a table. So we've pretty much already talked about this, except for now we're looking at it in terms of a real world situation. So we have this table and it shows us that the number of ounces connects with the cost of postage. So the number of ounces in this case is going to determine how much our postage is. So if it's 1 ounce, we know from the table that it's going to cost us 35 cents. 2 ounces will cost us 55, 3 ounces will cost us 75, and 4 ounces will cost us 95. Right? So in this case, we know how to go through and find all of our pieces. We are going to write this rule as a, what did we decide here? An explicit rule, because it tells us right up at the top that it wants an explicit rule. Oops, I didn't mean to erase that. I meant to highlight it. Right, so we're writing an explicit rule, so we know that we have to find our f of 1, which is 35 hundredths, and we're going to take that and plug it in, and then we have to find our common difference. So to go from each of these to the next, I add 20 cents. So I take my common difference, and I have to multiply that by n minus 1 because it's my explicit rule, and then I want to know, so the question asks me, how much would it cost for a 9-ounce letter? So what it says here is f of n being the number of ounces, is equal to, well, I shouldn't say n, I'm going to put in 9 right off the bat since I have less space. So f of 9 would be equal to my 35 cents times that difference of 20 cents times 9 minus 1. And then when I go through and solve that, I find that it'll cost me $1.95. Okay? So again, you're doing the exact same thing that we did in the previous lesson, except for now we're connecting it to real-world scenarios. All right, so now we're going to do this a little bit more on our own, or a little bit more independently. So first, we're looking at a table of the cumulative total interest paid in dollars of a loan after each month. So in the first month, they have paid $160 in interest. In 2 months, they've paid $230 in interest. And in 3, they've paid $300. 4, they've paid $370. So again, we have to go through, and first we have to find the common difference, which in this case, let's use this one here. We know that to go from 300 to 70, we have to do plus 70. Does it work here? Absolutely. Does it work here? Absolutely. You can start with whatever sections you want to find the difference. And then here I chose this one because it was easy. It's easy to do 370 minus 300. So I started there and then checked to make sure that all the others were the same. So I'm actually just going to say I'm not worried about that. And then I know that the common difference in this case is 70. Right, and then I also know that my f of 1 is 160, so I'm going to substitute 160 for f of 1, and I'm going to substitute 70 for d. All right, and then because I want to write it as an explicit rule, I know that it's my common difference that I'm going to multiply, and I'm going to add it to the same number each time. So I'm saying that if I start with 160, here, to go from here to here, I would have to add 70, but to go from here to here, I would have to add 70 twice, so 2 times 70. That's why we use the d times n minus 1. So it's kind of like if I start in the first position, and I want to go to the second position, I'm not multiplying by 2, it implies that I'm moving 2 times. This tells me how many times I'm moving. So 2 minus 1 tells me I'm moving 1 space, so I'm multiplying by 1. 3 minus 1 tells me that I'm moving 2 places, so I have to multiply that common difference by 2. All right, so that's why we use that. And then here, I plug in my values. And then now I want to find f of 20. So when the number of months, because remember, this is your number of months, this isn't our answer right now. So when my number of months is 20, I want to know how much interest this person will have paid. So again, I have my 160 plus 70 times, and this would be 20 minus 1, which we know is 19. All right, and just to quickly solve this, we're not going to do all the math of it, but it would be $1,490. So we know that the cumulative total interest paid after 20 months is $1,490. Again, you've done this. It's just now putting it into actual situations. All right, so then now here, when we are talking about, modeling arithmetic sequences from a graph, same idea. So typically what you will do is you can take your information from the graph and put it into a table that lends itself nicely to finding the common difference, because a lot of times students will make the mistake of trying to find the common difference and mixing up the numbers. So if you're not given these numbers like this, like here, I can find the common difference just by saying, okay, 37 minus 18 is 19, and then from here to here, do the math is 19. So we can do that, but when you're not given the numbers themselves, when you're just given, so here's your ordered pair, you're going to want to create a table. All right, again, you're going to create your explicit rule, so you need to know the common difference is 19. You need to know that your f of 1 is 18. Okay? And then you plug in 18 for your f of 1, and you plug in 19 for your common difference. Right? So we have to look at the information in this, not just how we put the information to use. So looking at the next problem, I have Eric who collects stamps, and the graph shows the number of stamps that Eric has collected over time in months. According to this pattern, how many stamps will Eric have collected in 10 months? All right, so here's the deal. The number of stamps collected depends on the number of months. So time is your independent, and the number of stamps is your dependent. So that's how we set up our graph. And then here, since my independent variable is time, that tells me that n is representing the number of months, and that f of n, after I use the function, so when I use n in the function, it will give me the number of stamps. Right? And now here, I can just go through and say, okay, this is 20, this is 33, this is 46, and this is 59. And then to do the common difference, I'm just going to follow along with what they say to make it easy. I find that it's 13, and that is the case from here to here. So I substitute 20 for my f of 1, because in the first month he has 20 stamps. Now he hasn't collected 20 stamps, he has 20 stamps. And then I substitute 13 for D, and then my function would be 20 plus 13 times n minus 1. And now the question asks me, how many stamps would he collect in 10 months? So I know that 10 has to go in for n, since n is the number of months. Okay, so then 10, so n is equal to 10, and then f of 10 is going to give me my answer, and this is my term. Okay, so that is my term, and this is my position. So for my position in this case, it's based on the number of months. All right, so f of 10 is equal to 20 plus 13 times, well, 10 minus 1, because 10 is what we're putting in wherever n is. So times 9, and again, we'll just quickly do the math and get 137. So if this pattern continues, Eric will have collected 137 stamps in 10 months. Okay. The reflection question asks you, how would you know which one's the independent and which one's the dependent variable? Right? So the independent variable indicates the term of the sequence, so it will usually increase by 1. So like if you go back here, time went up by 1. That's usually your independent variable. That's a good rule of thumb to use. However, if you go through and you use your statements and say, okay, does the number of stamps depend on the number of months that I'm collecting? You can also work through it that way. All right, and now for the last example, we are going to model arithmetic sequences from a description. So now we're not given the table or the graph. We are going to have to just do it from the problem. So the odometer on a car reads 34,240 on day 1. Every day the car is driven 57 miles. If this pattern continues, what will the odometer read on day 51? Okay, so now in this case, we know the odometer reads 34,240. And every day the car is driven 57 miles. Okay, so F of 1. F of 1 is the very first position. In this case, our positions are our days. So on the very first day, the odometer told us it was 34,240 miles. So that is our F of 1. Right? And then we're not given a table, we're just given this little bit of information. But if we know the car is driven every day, so we know that after this, the car will be driven 57 miles, so this will go up by 57. Then after this, the next day, it'll go up another 57 and 57 and 57. So we can say that 57 is our common difference. Okay, so then now we can start to write our explicit rule because we know our F of 1 and we know our common difference. Now the question was, after day, and I said 151, oh my goodness, after day 15, I apologize for that. So we want to know when the number of days is 15, how many miles will be on the odometer. So now I have to think, what's my independent, what's my dependent? Well, my independent variable is going to be my number of days. That's what's going to go up by 1 all the time, and that's just, the number of days doesn't really depend on anything. Time is just going to go on, and days are going to go on. Or actually, in terms of this, days don't depend on anything because days are just what we're working with. If we were talking about the number of days in a month, then we're talking difference in independent and dependent. Here, the dependent variable, so the number of miles, is going to depend on how many days the car was driven. So I know that my n is going to be my number of days, and then my number of miles will be what I get when I do f of n. So I want to find f of 15 because I want to know how many miles I will have driven in 15 days. So I replace that n with 15. Okay, again, my f of 1 is 34,240. Oops, that's supposed to be a 4. Plus my common difference, which is 57. Now I want to know f of 15. These numbers don't change, so 34,240 plus 57 times, so for this, it's the 15 minus 1, which is 14. And then if I do the math, which again is, I know you guys can do that, so I'm just giving you the numbers here. So on day 15, the odometer will read 35,038 miles. Okay, and then now to justify and evaluate, we can use an arithmetic sequence model. And it is reasonable because the number of miles on the odometer increases by the same amount each day. Okay, so by rounding and estimation, if I take 34,200 plus 60 times 14, so I'm rounding these numbers, I'm making them more compatible, I would get 34,240 200, because I'm rounding, plus 840. And I know that gives me 35,040 miles. Right? So in this case, my answer was 35,038. And since my number of days went up, but my number of days went down, but my number of miles each day went up, this does make sense. It is a reasonable answer. If my answer had been like 45,000, then I know that my answer would not have been reasonable. Okay, so 35,038 miles is a reasonable answer. Okay, so again, you're using everything that we've already done. You're just now putting it into that real world context. So again, just make sure you're identifying your important pieces of information and then figuring out, okay, which one's my independent, which one's my dependent. My independent is always my n. My dependent is always what I get, so my function of n. Okay, so you have 6 you-try problems that I would like you to do. I would also like you to do number 12 in the elaborate. I would like you to answer the essential question check-in. And as always, if you have any questions, please be sure to email me or write them down so we can go over them in class.